So we will now look into yet another equation which is building on the first equation, Laplace equation. So now we are going to extend Laplace equation to the Poisson equation. As we know, in the Poisson equation we will have the right hand side term. So let us start looking into the equation itself. So initially we had the term del square phi equal to 0 in the case of Laplace equation. Right now we are going to look into Poisson equation. So we will have del square phi is equal to rho by epsilon, and again when you look at the units, so we are talking about units volt per meter square. So this is going to be the unit of this right hand side term, and we are going to put certain value. So if we assume that rho by epsilon is equal to a constant at certain points, we can basically assign that constants in the domain. So it need not be a constant, it can vary across the domain. So what we are going to do is, so this is a special case. If this is a constant, then you can define the entire domain with certain rho by epsilon, whereas in our case we are going to keep this one as variable. So if you choose this path, then you can assign the entire domain with certain value for rho by epsilon, but if you choose the path of the variable, then the function, so this is going to be, let us say, a function f is equal to rho by epsilon, and f is going to be a function of x comma y. In other words, along the domain it is going to have certain values. So what we are going to do is, we are going to say at certain point we are putting the potential in terms of rho by epsilon. So in certain point we are assigning the source function to be certain value, and the rest of the points we keep them as 0. So in the example what we are going to have, we are going to run the particular simulation, and let us define the domain boundaries accordingly. So we have 0 comma 0, we have 10 comma 0, we have 10 comma 10, and we have 0 comma 10. So this is going to be the domain boundary, and we are setting all the boundary conditions where phi equal to 0. Of course we can set certain other boundary condition as well. For in this particular problem we are going to set all the boundary conditions going to be equal to 0, and the right hand side term which we are saying to be a variable, and we are assigning that variable to have certain functional values depending on the x and y coordinates. So let us take this further, and we say we will assign certain values for the source itself. So source is going to be defined as f of x comma y, and let us say at the point where f of x equal to nx by 4 and y equal to ny by 4. So we are going to define the value of the source at 2 points. The first point is going to be f of x equal to nx by 4 and y equal to ny by 4, where we are going to set the value as 3000 volts per meter square, and let us say we are choosing another point where x equal to 3 nx by 4 comma y equal to 3 ny by 4 equal to minus 3000 volt per meter square. So if you look at your domain, nx and ny are going to be number of steps. So these are number of steps in x, similarly this is going to be number of steps in y. So now what we are saying that for certain 2 points, and we have chosen 2 points in such a manner that it is going to be in a linear line and they are going to be at 2 locations, and those locations are given by these 2 points, and we are assigning certain value for the source. So let us go into the code itself and we will see certain parameters that we are declaring in the code. So this is going to be the Matlab program for solving a simple 2D Poisson equation using finite differencing method, and we are going to use a second order central differencing method like the way we discussed in the Laplace equation problem, and we are going to use the 5-point differencing scheme. So let us look at the initial specifications of parameters. So the length is going to be 10 in the x direction, 10 in the y direction, and the number of steps in the x and y direction are going to be given by nx and ny. In this case we are choosing 100 steps in each of the direction, and we are going to iterate the problem for 1000 steps, and the spatial discretization in x and y directions are going to be given by dx and dy, and each of the points in the x and y directions are going to be given in the vector x and y, which goes from 0 to Lx, which is 10 in our case, and 0 to Ly, which is also 10 in our case, and going to have a step size of dx defined by this particular equation. And now we are going to define the source term itself. So we are saying that the source is going to be a function of x and y along the entire domain. Since we assume that f is going to be a variable, we are defining it in each of the points. If we say that f is going to be constant in the entire domain, we do not need to do that, we can directly say f is equal to that particular value we want. But in this case we have taken a more complicated problem where we have said f is going to be a variable in the entire domain, and as we said we are going to keep the value of f source function as 3000 volt per meter square in 2 of the points. So in one point we are going to keep it as 3000, in the other point we are going to keep it as minus 3000 volt per meter square, and we are going to initialize the condition for the potentials and the boundary conditions. Like in the case before, we are going to put them all equal to 0. Of course we can vary the boundary condition as we want, but in this case we have set it to 0. Since we have defined the boundaries on the first and the last points, we are going to run the iteration only for I equal to 2 to nx minus 1, similarly j equal to 2 to ny minus 1, and the iteration goes except for this particular term. The entire equation is same as Laplace equation. In the Laplace equation the source function is going to be 0, so this is not there, whereas in this case we are going to have it on the right hand side. So when we are going to see the differencing analog of this equation, what we get is dou square phi by dou x square plus dou square phi by dou y square is equal to f of x comma y, which is nothing but the rho by epsilon. And when you are using the central differencing scheme, as we have seen, this will be equal to phi of I plus 1 comma j minus 2 phi of I comma j plus phi of I minus 1 comma j divided by del x square plus phi of I comma j plus 1 minus 2 phi I comma j plus phi of I comma j minus 1 divided by del y square is going to be equal to f of x comma y, which is equal to f of I comma j. And now when you rearrange the term, you are going to get on the right hand side the f term as well, and that is what you see in this particular equation here. So now we are going to plot the same function p which we are computing, and we are going to look at it from the top angle 0 comma 90, and let us simulate it. What we see here is the potentials on the left and the right, similarly at the bottom and the top they are all set to 0. What we see is two sources which are sitting in 2 points. So what you see is the solution what we have simulated. Maybe one test condition is if we can reduce the resolution, and we can see what is the impact of the resolution, like the way we saw before. Instead of having 100 steps, let us say we are having only 10 steps in nx and ny, and we are simulating it only for 100 iterations. You will see that the result is very crude, and you can already see the result will have certain pattern of the discretization in the way we see the potential distribution. This is not very accurate, as we can already appreciate that we already see the discretization impact in the solution. If I zoom it, you will be able to see it. What you see is pretty much the discretization impact is seen, and when we reduce the number of term even further, we will see that we are not able to get good results. For example, if I go even lower, let us say I am having only 5 steps in nx and ny, this is not accurate. As you see, the other side, the other source function is not able to be seen at all. So what we wanted to showcase here is, even though the differencing method itself will have certain impact, this impact is even more strongly seen once you have certain number of cells assigned. For example, if we increase the resolution, we will be able to see that we are able to get much more finer results. So if let us say we go for 150 cells in the x and y direction, you will be able to see that we are able to very accurately replicate the potential, and this is what we want in our simulation method, that we want to have a good resolution. At the same time, we have to compromise on the number of iteration. When you are doing simple problems like this, the most important thing is to make a good sense of judgment. How many iteration do I need, what is the number of cells I need in x and y direction, and also what is going to be the method I am going to use. In this case, we have chosen central differencing scheme because it has a better accuracy than forward and backward differencing, which we saw in our earlier modules. However, only using central differencing scheme is not enough. We need to set certain parameters like the spatial discretization in x and y direction, and also the number of iteration what we need to resolve this problem. So we have showcased a classical problem of Poisson for understanding how a simple problem can teach us a lot about finite differencing method. I would encourage you to take this code and practice it for yourself and play a little bit with various parameters, so as to get a physical sense of what we are simulating and how we can use this information and knowledge for solving much complex problem at later stage.